So we're going to pick up with this example for freezing and boiling point. This is Chem 102, Chapter 13. We're in Section 5, I think. So why don't you take a look at this problem? So ethylene glycol is an antifreeze, water-soluble and fairly non-volatile, meaning it has a boiling point that's pretty high. Calculate the freezing point and the boiling point of a solution containing 685 grams of ethylene glycol in 2,075 grams of water. See if you can use your formula sheet to find an equation that would work for this. And in the formula sheet, you have an extra letter we haven't looked at yet in your equation. So just ignore that letter for now and use the formula. So if you haven't found it yet, formulas that you can use are delta TB is equal to, we're going to ignore that I for now, KBM. And delta TF is equal to KFM. So go ahead and pause and work it out. So hopefully you're able to work this out. You have your delta T, which is your change in your boiling point, is equal to, oh, I need to give you the information, sorry. So if you paused, sorry, you can't really pause yet. You need the KB for water. And we need the KF for water. And again, and the reason in the textbook is assuming that you have this table here. So your KB for water is 0.51 degrees per molal, and your KF is 1.86 degrees C per molal. Now you can pause and work it out. Go for it. Okay, so assuming that you did pause and work this out, then we have our delta TB is equal to our KB, which is 0.51, times our molality. We got to figure out what the molality is. So let me move this down a little bit. Let's find our molality. Remember that molality is going to be equal to moles of the solute over kilograms of the solvent. Now, how do we know which one is the solute and the solvent? Which one is more, which one is less? So way more water. So that's going to be our solvent. So our solute is going to be the ethylene glycol, which means we got to find moles of it. So 0.685 grams, and I'm just going to say EG for ethylene glycol. I go in my calculator, I'm going to find a molar mass for this guy. Formula is rather large, so try and, if you can, to get really good at using your calculator's parentheses to calculate molar masses. So I have 2 carbons. I have hydrogen times 1, 2, 3, 4, 5, 6. And I have oxygens times 2. So I should get 62.08 grams of ethylene glycol. And that's going to give me moles of ethylene glycol. I get 11.03414 moles of ethylene glycol. Again, I like to give myself lots of numbers so that I'm not rounding yet. I would round to 3 sig figs, so I'll just underline those as a little note to myself. And then I want kilograms of solvent. So if you're good at the SI system and you can bounce the decimals around, go for that. If not, just there are 1,000 grams in a kilogram. Don't be afraid to just do a little dimensional analysis to work it out. All right, and then again, we'll make sure we keep our 4 significant figures here. So we have our molality. It's going to be 11.03414. Just actually kept that in my calculator. Divided by 2.075 kilograms of water. I get a molality of 5.317662 M for molality. Remember, this was 3 and this was 4, so this one will be 3 sig figs. So when we put this in with for our boiling point, we would get 5.31766 molal, 3 sig figs. For significant figures for your constants, usually we don't count them as significant figures, so we would keep that 3 significant figures there. I keep this number in my calculator and just multiply it by 0.51, so I'm not retyping everything. So 2.71 degrees C is our change in boiling point. So our new boiling point would be 100 degrees C plus 2.71. And we would assume 100 has more sig figs because we could say 100.000000 to infinity, right? So let's write 102.71 as our answer to keep the same number of digits after the decimal as our 7-1 here. So we would keep those numbers because ideally the boiling point is exactly 100. It may be that if on the test or something we do look for significant figures, we may give you the boiling point as like multiple digits. Could there be more numbers over here for yes, but so just watch when you're doing Alex. If they do give you the values, you may want to just use the information given. So if we did want to use that, then we could say 102.7. See what the textbook wants us to use. And then we have our freezing point. So notice we added to the boiling point because we were doing the boiling point elevation. And so for freezing point, our molality stays the same. We get 9.89 here. And we're going to subtract that from our degree C. So our new freezing point is negative 9.89, or maybe they want us to put negative 9.9, depending on if they want to use 0.000 to infinity, or if they want to use 0.0 or 100.0, because that's what they have in this table. So we have to just kind of go by what we think the textbook is looking for. I would say if you had to guess, use what they give you in the table for significant figures, because boiling points technically are measured, even though we kind of know that the one for water is pretty close to exact. So it looks like they use the significant figures here. So in Alex, use 1 digit after the decimal for your boiling point and your freezing point. Oh, for this one, they just use 0. They didn't even use 0. They didn't even use 0.0. So it's not very consistent. So hopefully in Alex, they won't give you too much trouble for the significant figures of that. But let me know if you do need me to look at it and tell you what to put in. Just text me. Okay, osmotic pressure is the pressure that stops osmosis. So what's osmosis? Osmosis is the passage of a solvent through a porous membrane that the big solute particles cannot pass through. So if we have a membrane where smaller water molecules, for example, can pass through, but big solute molecules like glucose or something cannot pass through. The flow of solute or solvent particles is going to be from less dilute from more dilute to more concentrated. So basically water always wants to be part of the party and is going to say, oh, there's a lot more concentrated on the right side. So it's going to flow toward the right side. Notice that the amount of liquid in the left side goes down and the amount of liquid in the right side goes up when we see a difference in these two images. So we're diluting the right side. And you can see the color change there helps you visualize that that's been a dilution that's happening. Water would theoretically just keep going until there's no more water left in the left side and all of it is over here in the right side, because water really wants to go until the concentrations are the same on both sides. And if this side is pure, concentration could never be exactly the same, so it will just go as much as it can. However, something stops it. So we have this atmospheric pressure pressing down on us, and then there's actually like just pressure of the solution on this side. And so we get to a point where it stops because the pressure kind of pushing down from all the water being on this side keeps the water from being able to flow over. So we had this flow over and it will stop that. And so we can actually calculate the difference in these heights of these tubes can give us the pressure in like millimeters. If it's millimeters of mercury or millimeters of that water difference there, can give us the pressure. Call that the osmotic pressure. Osmotic pressure is by the symbol of pi, and it is related to the molarity, concentration of the solution. The gas constant, this is your old gas constant with the liters and atmospheres, moles and kelvins, and then the temperature, of course, in Kelvin to match the units of R. So you can see how we can get moles per liter out of that gas constant there. So this is just another formula. We could use that formula to calculate the molarity of a substance after it has gone through the osmosis process. So like perhaps I know what the molarity of this substance is, but once we get to this point where we stop, I don't know what the molarity of that substance is anymore, right? Because I know that some water came over, so it's definitely more dilute, but like I don't really exactly know how much more dilute it is. So we could use this to calculate what that new molarity is. So one thing about solutions, and specifically electrolyte solutions, so electrolytes are substances that conduct electricity, solutions that conduct electricity. And they undergo dissociation when dissolved in water. So dissociation means breaks into ions. So we have strong electrolytes. Strong electrolytes are ionic compounds. And strong acids. If you don't know a lot about strong acids now, we will definitely cover that in a future chapter. And then we have weak electrolytes. So strong electrolytes, they break 100% into ions. Like they don't even have any molecules left. Weak electrolytes are weak acids or weak bases. And these break partially into ions. And then we have non-electrolytes, which are covalent compounds. No acids or bases. We don't break at all. 0% breaks into ions because it doesn't make ions. It's just covalent. So sugar, for example, is a non-electrolyte. So if you're like, hey, I really need electrolytes, one of the first ingredients in Gatorade is sugar. So it may not, sugar is actually not acting as an electrolyte. So because when we're looking at the molarity of a substance, we actually need to think about, well, it's the molarity of the particles that really matter for colligative properties, right? It's the amount of tiny little particles we're making that matter. And so we need to be able to factor this in. So the Van 't Hoff factor, or I, accounts for the fact that things are actually going to break apart into ions sometimes. And so it will get more particles in that solution than just what we measure out as molarity. So in like, for example, in a 1 molar sodium chloride solution, we get 2 molar ions because we have a sodium and we have chloride ions. So there's twice as many ions as there are individual sodium chloride ions. So we might weigh out and measure out in lab a 1 molar sodium chloride solution and then find that it affects our boiling point in a way that's more than what we expected it to. That's because the Van 't Hoff factor wasn't taken into consideration. So the Van 't Hoff factor is basically the actual number of particles in solution after dissociation versus the number of formula units initially dissolved in solution. So we can think about it as I as being the actual or experimental concentration of ions over the prepared concentration of ions. So what did we make? We made a 1 molar solution, right? So in my example up here, I'm thinking I made a 1 molar solution, but I actually have 2 molar ions being in that solution because each sodium chloride broke apart into 2 pieces, so it's twice as much. So my I would be 2. And so we just stick I at the beginning of all of these formulas because it will affect in that proportion. So if I have concentration of this and I have twice as many, I'm going to be doubling the concentration. So my I would be 2, for example. Same thing here. That's my molarity of my solution. The I would be double that. So Van 't Hoff factor is 1 for all non-electrolytes. Because when you take a non-electrolyte and we dissolve it in water, it does not break into more particles. It stays as a molecule. So if we take sucrose, which is this substance, C12H22O11, if we take sucrose and we break it, we dissolve it in water, it's only going to break into molecules. It's not going to break into ions. So it'll just be like solid sucrose goes to aqueous sucrose. So water is going to surround each sucrose molecule, but it's not going to break it down into like carbons and hydrogens and oxygens. For strong electrolytes, like ionic compounds, the I should theoretically be equal to the number of ions. Because it should be that clean ratio that I just explained. Like if I put 1 molar in of sodium chloride, technically I should have 2 molar concentration of ions. And so it'll be 2 divided by 1 to give me that I. So it'll be 2 dissolved particles. So theoretically the I is just the number of particles you're going to make when you dissolve. Do you dissociate into ions? Then your I will be greater than 1. If you don't dissociate into ions, your I is going to be 1. For the sodium sulfate here that we're looking at the bottom, it should break into 3 ions, 2 sodiums and 1 sulfate. Now keep in mind the sulfate is a polyatomic ion. It's not breaking into sulfur and oxygens. We're not breaking apart into individual atoms. We're breaking apart into ions. So just how we would know to call this sodium sulfate and not sodium sulfur tetroxide or something like that. We have to know our polyatomic ions to be able to recognize how our ionic compounds are going to break apart into pieces. We're not going to separate the polyatomic ions into pieces because polyatomic ion just is that thing. It's a covalently bonded substance that has a charge. So if we make 2 sodiums and 1 sulfate, my I would be 3, theoretically. However, it's usually smaller, this Van 't Hoff factor, than we think due to the formation of ion pairs. So ion pairs, basically, ions don't want to separate. They're attracted to each other, so sometimes they don't separate. And so theoretically, we would think that they would separate 100%. Even in strong electrolytes, we think that they would separate. However, sometimes they don't. So in real life, they sometimes stay together. And so our Van 't Hoff factor is sometimes smaller than we think it's going to be because some of our ions are going to stay together and they're going to stay chunked together. So we can calculate our Van 't Hoff factor. And for non-electrolytes, it's going to stay the same because we don't have that ion effect, right? So 1 is not going to become less than 1. But for anything that's ionic or acidic, which acidics make ions, acid acids make ions, you're going to see that it's going to be a little bit lower. And you see that as you increase charge, so if we go from positive 1 and positive 1 and negative 2, we only decrease a little bit. But if we go from positive 2 to negative 2, we decrease more. And if we go from positive 2, so positive 2 to negative 1, decrease a little bit. Positive 3 to negative 1, decrease even more. So it's kind of like lattice energy in the same way, right? If you have a more positive and negative ion, then they'll attract more to each other. So they'll clump together more. So they actually make fewer particles than we think. So instead of making 2 particles for every 1 magnesium sulfate, we actually only make an average of 1.3 particles for every magnesium sulfate because they stick together. And so as we increase the concentration, we actually get worse with our differences in Van 't Hoff factor. So The higher the concentration, the bigger our difference is, because the more ions we have kind of clustered together in concentration, more concentrated, the more they're going to stick together. So think about like if they are closer together, they're more able to, like if your magnets are closer together, they're more able to come together and clump together. If they're farther apart, they're not going to clump together as much. So higher concentration is going to decrease your Van 't Hoff factor more. So if we are trying to determine the experimental Van 't Hoff factor, I want to work this one through with you. Basically, we have to remember, or I'll let you work on it, but let me give you a hint to start. So remember that your I is going to be your actual experimental concentration over your prepared concentration. So our prepared concentration here would be this. We prepared this, right? We made a concentration of 0.01 molar potassium iodide. So what is the new concentration? Well, we can use the osmotic pressure to tell us that. So osmotic pressure is equal to MRT. And we don't have I, right? So we can't put the I in there. We can put in what we think I would be, which we think it's going to be around 2. But again, this is wanting us to actually discover the experimental Van 't Hoff factor. So I guess this would be your experimental Van 't Hoff factor. Your theoretical Van 't Hoff factor is easy to find because you just look at the number of particles that you make. And so we need to find this M because this M would be our actual experimental concentration. And that would go in the top. So why don't you solve for M and then see if you can put that together to get I. All right, so to solve for M, M would be equal to osmotic pressure over RT. So our osmotic pressure is 0.465 atm. Your R is 0.0821 liters times atmospheres over moles times Kelvin. And so therefore our temperature needs to be in Kelvin, so 225 degrees C plus 273.15 would give us Kelvin. Make sure they're using, yeah, they use 206. So we'll say 206 here. You have 206 on your equation sheet, good. But just to make sure our math matches. And again, I'm lazy. I'm going to just put that Kelvin temperature conversion in my calculator like that. So I'm going to subtract, I'm going to divide. So 0.465 divided by 0.0826. It's going to cancel out my ATMs. And then I'm going to say divided by, parentheses, 25 plus 273.15. Remember, if it's in the bottom, it needs to get divided. This will cancel out my Kelvin. So I will get 0.0190, and it's going to be 1 over liters over moles, which is equal to moles over liters, which is equal to molarity, right? If you divide by a fraction, you multiply by its reciprocal. So keep an eye on your units there, because I can really help you make sure you have the right numbers. This is our experimental. So osmotic pressure says, hey, we actually have a concentration of 0.19. We prepared a concentration of 0.01. Why is it bigger? Well, because it broke into pieces, right? We prepared this much, but it broke into some pieces. Now, maybe it didn't break into twice as many pieces because we would expect 0.02. It's not quite 0.02. That's okay. So our I would be our actual concentration that we found from the osmotic pressure measurement over our prepared concentration, what we thought we had made. And we noticed that, hey, we have a bigger concentration than we thought because the particles broke down into pieces. So our I is 1.9 here. So my experimental Van 't Hoff factor is 1.9 versus it should be 2 if it broke apart perfectly. should be twice as much concentration there, but according to our osmotic pressure, we actually didn't get the perfect amount of potassium iodide separated. So I hope that makes sense. So when we're using colligative properties, we can use a couple of different, another couple of terms. Percent dissociation is the percent of dissolved molecules, or formally units, that separate into ions. So, well, if we thought it was going to be 100% breaking into ions, maybe what was it, right? If we thought it was going to be 2 here, that's on 1.9, well, what percentage of that actually dissociated, right? That's going to be percent dissociation. Strong electrolytes should have complete 100% dissociation. However, we know that's not necessarily the case. And so we know that we get closer to 100%, closer to the theoretical Van 't Hoff factor if we're at lower concentrations. So at lower concentrations, the particles aren't as clumped together and they're less likely to make those little ion pairs, and we'd have better dissociation, better breaking apart. It has got more room to separate, if that makes sense, if it's at lower concentration. And percent ionization is also dependent on concentration. So lower concentration gives you more ionized. So weak electrolytes, they don't ionize 100%. They don't dissociate 100%. So we can call that percent ionization, the same kind of thing as percent dissociation. So here's an example. Quinine is the first drug used to treat malaria. It remains the treatment of choice for several severe cases. A solution prepared by dissolving 10 grams of quinine in 50 milliliters of ethanol has a freezing point of 1.55 degrees C below that of pure ethanol. Determine the molar mass of quinine. So let's assume we don't know the formula. We can't use the periodic table. We want to know the molar mass. I gave you the density of ethanol. We are assuming quinine is a non-electrolyte. We know the freezing point change, and we know how much quinine we put in and how much ethanol we have in there. So go ahead and give it a try. I know it might be a lot for you to do the whole thing, but just get information what you can and then unpause it and then pause it again if you feel like you get enough information to then try it on your own. All right, so what's our information here? We have 10 grams of quinine. I'm just going to say Q. We have 50 in 50 milliliters of ethanol. We abbreviate ethanol ETOH sometimes. We have a freezing point of 1.55 below that of pure ethanol. So they're not actually giving us the freezing point, they're giving us the change in freezing points. The change in freezing point is 1.55 degrees C. I want to know the molar mass. So molar mass can be written as this fancy M here of Q, which would be moles of Q divided by, whoops, just kidding. Molar mass is mass per mole. So grams, or let's say mass in grams of Q over the moles of Q. Well, we already have the mass of Q. We know this is how much mass we have. So we have this part. So really, we just need to go and find the moles of quinine here. Well, this can give us a hint. Oh, we also have the density. Sorry, density of ethanol, ETOH, is 0.789 gram per milliliter. So this hints to me, and I know density is equal to mass over volume, but of ethanol. So this would be mass of ethanol, ETOH, over volume of ETOH. So be careful with your density. It can't just be like mass of the quinine over volume of the ethanol. It's got to be the same substance top and bottom for density because it's for a pure substance. Well, I know TF is equal to I KF M. Let's assume for this problem we could go and we could find a KF value. Let's see, because I don't think they're asking us to find that. So go up into our table. Let's find the KF of ethanol. So KF of ethanol is 1.99. And again, you would be given those pieces of information on a question. 1.99 degrees C per M. Okay. So I know my I is 1 because it's a non-electrolyte. They tell me that. If it's not an electrolyte, we don't have to worry about that experimental or anything. It's not breaking into ions. We're not going to get any of those ion pairs or clumps. We know it's going to be just 1. So I have my KF, I have my I, and so maybe I can solve for molality. If you're not sure what to do, let's just solve for something that we can solve for. So let's solve for molality. Molality, and this is going to be the molality of the solution, right? So molality is going to be equal to moles of quinine over kilograms of the ethanol, because that's my solvent. Oh, look. If I can find the molality, that gives me moles of quinine, right? So just by writing out, what do I have? What does that mean? I have density. What does that mean? Right? If I know this is going to be grams of ethanol over milliliters of ethanol, how can I find kilograms of ethanol? Well, if I can find grams of ethanol, I can find kilograms of ethanol. Well, did they give me volume of ethanol? They sure did give me volume of ethanol. Let me just highlight that in a different color so you can see. So I'm kind of piecing together here what I might be able to do with this information. Now, I think that this part of writing things down and trying to piece things together is really helpful in a problem like this, because a problem is not going to sprout legs or a mouth and tell you, hey, do this first. Just organize the information that you have and see if you can make any connections from what you have to what you want. And writing it out, what do I want? Molar mass. Okay, well, what is that? Mass of this over moles of this, but not just mass over moles. We got to look at what substance you're talking about, because we got 2 different substances here. So I'm going to be labeling my substances pretty clearly here. So if I can find the molality, right, I can actually find my moles, because I have my kilograms of my ethanol I can find through the density. And then if I can find my moles, I can plug that in and get my molar mass, which might help me actually figure out what the formula is. Because if I remember, if you did empirical formula stuff, remember, we could find the empirical formula using an experimental mass spectrometer report, and then we can find the actual molar mass of a substance, then we can get the full formula. So if we start by just finding our molality and plug in, molality is going to be equal to delta TF over I times KF. And again, I like to rearrange the variables first before I plug in, because that saves me a lot of time on the test. I know my delta TF is 1.55 degrees C. I know my I is 1. And I know my KF is 1.99 degrees C per mole. This cancels out my degrees C, and I get 1 over mole, which is just mole, which is what I want. So my molality is going to be 1.55 divided by 1.99. 0.77889 And this is going to be, again, moles of quinine over kilograms of ethanol. And we'll work our sig figs here, should be 3, just to underline as we go. All right. We can use this as a conversion factor. So anytime we see this slash, or you know there's 2 different units of something, you can use it as a conversion factor. So let's figure out how many grams of ethanol should we put in. So if I start with kilograms of ethanol, writing this wrong, ECOH, then technically, right, I could say 1 kilogram of ethanol is equal to 1,000 grams. Wait, whoops. Okay, 1 kilogram of the ethanol is equal to 0.778894 moles of quinine. And that would get me moles of quinine. So this is why I'm looking for the kilograms of ethanol. So let's find those kilograms of ethanol. And then if I have this, I can plug it into here, remember? So I know that there are 50 milliliters of ethanol. And I know that the density is for every 1 milliliter of ethanol, we have 0.789 grams of ethanol. And I know that for every 1,000 grams, there's 1 kilogram. So we cancel out our milliliters, cancel out our grams, and we have kilograms. But this will give me 50 times 0.789 divided by 1,000. Give me 0.03945 kilograms of ethanol. So I'll mark my sig figs as I work. Then I'll take this number and we'll plug it in right here. So we'll say times 0.778894. So that will give me 0.030727 moles quinine. And then we can find our final molar mass. Let's oops, look down here. So my molar mass is equal to, they gave me that 10 grams over 0.030727 moles. And this will give me the grams per mole. And divided by my previous answer. So 325 gram per mole would be my final answer. I know this is a lot of work. It's a lot of thinking, but it's not actually stuff that's very new. The only new thing is this formula, the change in the freezing point. Everything else is old stuff. I guess molality is also new, but you know what moles are and you know what kilograms are, and we know what density is. It's just recognizing how do I rearrange what I have to get what I want. And that's basically all we do in chemistry, right? So let me know if you have any questions. Try this on your own without, do it again on your own and make sure you can get it and come back to these notes if you need to. All right, so there's another problem here. So this problem is another molar mass problem. So this is of water and it's using osmotic pressure. So why don't you try this one? I'm not going to work this one out, but you should try it. And then the worked example here, so the textbook's giving you the answers. Let me know if you need any support if you're not sure how they got what they got here. Here's another one, percent ionization. I'm not going to go through this whole one in this video, but percent ionization, if you think about any percent, it's part over a whole. So for percent ionization, let's see. Oh yeah, this one is a little difficult. Let's save this one. Save this one for class. So we'll do in class. And then we will, I'll make sure to get that one in class. So last little bit here I just want to go over in this video with you is colloids. So colloids is basically, they're basically a solution, but their particles are a lot bigger. And so they're almost like heterogeneous because they've got big pieces, but they are spread out homogeneously. So it's like a mixture of heterogeneous and homogeneous. So it's like big particles that are heterogeneous kind of in nature that they would naturally just kind of settle down, but suspended for a moment. So different categories of colloids you are definitely familiar with colloids. Aerosols. So you spray something, right? For a moment, the liquid is suspended in the air. And then eventually it'll fall down and settle on stuff. Foams are colloids. Emulsions, if you do any cooking and you try to emulsify stuff, like mixing in things until if you mix enough like oil and vinegar and you mix it enough, it will emulsify to where it'll actually mix together, even though it shouldn't necessarily mix together. And what colloids do is the Tyndall effect. So this is the Tyndall effect. So like if you've noticed how vehicle lights are in fog, it's because fog is a colloid. So the Tyndall effect is that colloids have really big particles, so they disperse the light, and you can kind of see the light going through the solution or the substance. And versus normal solutions that have small particle sizes, they don't disperse the light, so you wouldn't see light through it. So if there's no fog, we don't see a stream of light. If there's fog, you actually would see like headlight would make like a line next to it. We call that the Tyndall effect. So here's some types of colloids to just look it through so that you kind of know, familiar with like, hey, what's a foam, a sol, an aerosol, a foam, an emulsion. So they're just different. You can have, just like solutions, we can have all different phases in all different things. So the medium means like the solvent kind of, and the dispersed thing that's being dispersed is like the solute. Colloids can have categorized as hydrophilic or hydrophobic. So hydrophilic means water loving, hydrophobic means water fearing. And this is how a lot of our biochemistry happens, right? So hydrophilic groups on the surface of large molecules stabilize the molecule in water. What do you notice about these hydrophilic groups? So these would be the hydrophilic groups. Notice that they have things that are similar with water. They've got ions, they've got charges, or they've got hydrogen bonding, right? And that's something that water understands. So maybe this protein has a bunch of nonpolar stuff in it and wouldn't really be transported in your blood very well because your blood is mostly water. But because we have these hydrophilic groups on the outside, now the protein can talk to things that have water in them, right? So it allows the molecules to be in water without totally breaking down. For hydrophobic colloids, you can have certain colloids like attract certain ions to them, and they can prevent aggregation of like pulling together of those articles, right? So if we don't want these two particles to kind of come together, then the colloid particles can actually attract certain ions to them. And so that can keep them from kind of clumping together. Hydrophilic colloids, hydrophobic ones can be stabilized also by hydrophilic groups. Again, we talked about we could have like a long hydrophobic thing and we have this little bit of hydrophilic thing. And so now it's okay to have at least part of it in water if we needed it to hang out there. This, you may notice that this kind of looks like the phospholipid bilayer, right? If you think about your cell membrane, that's exactly what's happening. Emulsification is just stabilizing a colloid by either wrapping it something. I know you've probably done this in cooking by just like stirring something a whole lot, breaking down some of those pieces. But we use these things called micelles for soap. It will take something very hydrophobic like grease and it can make it hydrophilic, kind of like a Trojan horse where we're kind of modifying or like hiding the hydrophobic stuff in the center and having the hydrophilic stuff on the outside so it will dissolve with water. All right, I will see you in class for the rest of this unit.